Hey there, awesome viewers! Welcome back to my YouTube channel. I'm Prav, and today I've got something really exciting to share with you. Before we dive in, I want to remind you of something important. Yes, you guessed it right, it's time to smash that like button, hit subscribe, and don't forget to leave a comment below. In today's video, I will show you how you can increase 10 times the speed to train your long short-term memory neural networks. This is the so-called LSTM networks. We will use Google Colab and we will enable GPU acceleration. I have prepared a very short example for you where we're going to train a neural network to recognize the pattern of a sine wave. The coding is at twice the speed for better watching experience, but if you want to see only the CPU versus GPU acceleration change, go to the last minute of the video. We start by importing the libraries for data processing and machine learning. Turn attention that we use Keras, and here import the LSTM network layer and the cuDNN LSTM. This is the CUDA-enabled GPU accelerated model layer. In the next cell, we're going to create the sine wave dataset with close to 8,000 data points. As an overview, we will first create the LSTM baseline using the CPUs, and then I'm going to show you how the performance improves when we use the GPUs. And now we have the sine wave plotted. In this next cell, we're going to write a function that splits the data based on predictors and target. Since this will be a long coding experience, I will provide you with a link in the description to my GitHub page from where you can copy the code. The function takes in the data and the parameters that determine the number of data points for training. This is the lag, or the so-called predictors, and the NI head steps we will predict. Here we're going to set up the parameters for the function previously and also for the model later. The lag will be 256 points, the NI head steps will be 128, the training data percentage will be 70%, the validation data percentage will be 10%, effectively the difference between the training and the 80% here. The test data set will be the remainder, 10 epochs, and batch size is 1. Now we're going to reshape and scale the dataset in preparation for the LSTM network. And we're going to feed it into the function we wrote earlier. Now the errors I get are because I didn't run the function earlier, and also I misspelled the lag variable. In the next cell, I'm going to show you how we can split the train data, validation data, and test data sets into predictors and target. I cannot emphasize enough how important it is to keep separate the training, validation, and test data subsets to avoid training leakage and model problems later. Now we will build the neural network code. We will start with a simple 16-node LSTM layer that uses CPUs. We will use the TAN-H activation function for like-to-like comparison with the GPU accelerated layer later. We're going to add a second layer with 8 nodes and the same TAN-H activation function before we add the output dense layer. The early stopping function is another feature you can use to speed up your conversions of your training with neural networks. After we completed the model, we will type in the code that takes the training and validation data and runs it through the model. You will see the speed of training the model on the CPUs, and we will leave this running in parallel while we type in a few other post-processing code pieces. After training the model is done, we will take the test predictor dataset, and after we feed it through the trained model, we will get the result, the predicted sine wave pattern. This will be stored in the y-hat variable. We will also need the actual data under the actual n ahead variable, against which we will try to compare the accuracy of our prediction. We will turn these to data frames and inverse scale them. You can see the model keeps running with an epoch taking between 50 to 60 seconds. After the model runs, we will need to plot the results so we can visualize them. So here we're going to write ourselves a plotly function. We will also write a function that captures a number of metrics to measure accuracy of the model prediction. It has taken more than 9 minutes to complete the training of the model and testing. And now we're going to run the results. Let's see the plots. So this is our baseline with the CPUs and the results. And now I'm going to show you how you can turn this and run it with the GPUs and how much faster it's going to run. When you're setting up the code, do not forget to select GPU under runtime. For changing the GPUs, we will comment out the code lines with the simple LSTM layers. And we're going to add the ones with the GPU enabled layers. With the paid version, Google Colab allows you to try the latest NVIDIA data center GPU chips, such as the H100 and V100. If you have the paid version, feel free to try them and let me know in the comments your experience with them. Now let's start a root kernel and run all the code. It's the moment of truth. You can see how much faster the model runs with the GPUs and produces fairly comparable results with the CPU model. I hope you agree now that the GPU accelerated LSTM networks are fun and easy to use for troubleshooting and fine-tuning your LSTM models. But you should also be aware that there's a limitation for the QDNN LSTM network, and that is that the 10H activation function is hard-coded. If you managed to make it to the end, thank you for watching, and I'll see you in the next one.